What classes am I teaching next semester? I don't know. You know, I usually don't find out until the end of the semester. Yeah. It's likely not going to be any of the grad courses, just because we have a few faculty going on sabbatical next semester, and so we need to fill their holes up for the undergraduates, and so I'm probably most likely going to teach 410, which is our undergraduate finite element class, and so it's kind of the undergrad version, the kind of the baby version of this class. I do always request fluid mechanics, and so that's 333. And so I would think that I would get that one too. And for my glass class, I'm not sure. But I am teaching it. I am taking a reduced load next semester too, because I'm taking over the academic advising for our undergraduates too. And so that'll have me teach only 3 classes instead of 4. So I don't think I'll be teaching any grad courses in the fall, but that might change. All right, it's 7 o'clock, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Doing good, I hope. All right. So thank you guys for meeting virtually today. I know it's a change from our in-person, but so I appreciate you guys' flexibility. So I did go see a doctor today, and the doctor thinks, because you know I've talked to some of you, I've been having some back problems for a while. My doctor thinks that it's a muscle strain in my butt actually, and so and so you can't see it. But right now I don't have any pants on, and I actually have an ice pack underneath my left butt cheek, and so one of the perks of working from home is that you can nurse your injuries while you work, and so I'm going to take full advantage of that today while I can, before I have to come back to work tomorrow. So yeah, hopefully after that things will be better. Okay. Okay, so the plan for today is we're going to continue on with our lecture notes on 2D finite elements, and so we kind of stopped right in the middle of a derivation, and so we're going to finish that up, and then we're going to start to apply it to the 2D heat conduction equation. Okay, and so the 2D heat equation, you know, you can kind of almost think about like, you know, we're going to be focusing on that for the rest of the semester basically, and so you know, obviously, you know, you're solving the 2D heat equation for your final project. And so that's going to be important there. And, you know, a lot of the mathematics and a lot of the methods that have to go into 2D, you know, we'll use the heat equation to illustrate all of those things. Okay. Okay. And so are there any questions I can answer before we get started? Okay. All right. So let's go ahead and pick up where we left off. And so, you know, let me just go ahead and scroll up here. Okay. It was a lot of math, I know. Okay. But the idea, what we were kind of in the middle of is that we know that when we get to, doing this in 2D, eventually we're going to have to perform integration by parts, right? So that was kind of a core component of our 1D finite elements, right? And so if we looked at the weak form of our, a 1D heat conduction or 1D structural equation, right? We had this kind of situation, and in order to get it into a form that we can apply finite elements, we had to apply integration by parts. Okay, and the main motivation behind that was to basically take this integrand, okay, which has our weighting function w as well as our solution function u, and then transform it into something with a more balanced derivative, right? And so we want to basically move one derivative onto the w and take one off from the u. Okay. And so that was a key part. And so, by reducing the order of the derivatives on our equation like this, we were able to make use of linear functions to solve for it, right? Either a linear weak form equation or a linear shape function for finite elements, right? And that ended up being a big boon for us because, with linear shape functions, we ended up with a very nice, very nice looking element stiffness matrix, okay, as opposed to quadratic. And so we were looking at how to do this in a multi-dimensional case, right? And so the vehicle of which we were going to do this is something called Green's theorem, right? And so the idea with Green's theorem is that it provides a way to take if we have a function and we have its gradient, if we have a region integral on that, or in this case we have a triple integral, we can transform that into an integral around the boundary, okay? And we were right in the middle of doing that for our case here, right? And so if we took our function here and we broke it up into components, right? And so we had the x component, the y component, the z component, right? We would have these expressions that form from Green's formula. Okay, I'm going a bit fast just because I want to kind of get through this. Okay, and we're right in the middle of applying this to this functional form right here. Okay. And so basically, the idea was that if we had this functional form, right? Because right now what we have is Green's theorem that's defined for just a generic function f, right? But for our finite element problems, we have something more specific than just a function f, right? So our function f here is going to be comprised of the product of our weighting function together with our solution gradient, okay? And if we apply that with Green's formula, then we obtain all of these expressions over here, right? And so we have the x component of it, the y component, the z component, okay? And in order to obtain Green's formula, or the multi-dimensional integration by parts, all we have to do is to take all of these components and add them together, okay? Oh my God. Sorry about that. Of course, it stopped sharing. I bumped the power button on my computer. Okay. Okay, and so that's where we left off. And so we're going to take all three components of Green's theorem here and add them together in order to obtain, Green's formula, or in other words, multi-dimensional integration by parts. Okay, so let's go ahead and add all of these together. So if we add all these together, okay, and we end up with the following. And so on the left-hand side, we have our triple integral, okay, based on the volume. First, we have the x component, and so we have partial w, partial x, and then partial t, partial x, plus w, partial squared t, partial x squared, okay, plus partial w, partial y, partial t, partial y, plus w, partial squared t, partial y squared, okay, and then the z component, and so we have partial w, partial z, partial t, partial z, plus w, partial squared t, partial z squared, dv. Okay, so that's all the triple integrals on the left-hand side. And on the right-hand side, we have our surface integral, right? And so our surface integral, we have double integral here. I put a circle around it to indicate that it's a surface one. Okay. We have W partial t partial x plus W partial t partial y. Okay. Sorry, this is dot nx, and the second one is dot ny plus W partial t partial z dot nz. Okay. And this is integrated over an area, so we have a dA right there. Okay. All right, so let's go ahead and rearrange these terms. Right, and so I'm just going to take all the terms of this expression and just kind of move them around a little bit, just to make it, just that we can make some simplifications. Okay. Right, because what you can see, if we look at this term, and this term, right, they all look very similar, and so we can go ahead and group them all together. Same thing with this one, and this one, right? And so since all those look similar, then we can group them together and simplify them just like that, okay? All right. And so if we do that, we have triple integral over the volume of W. First, I'm doing all the second order derivative terms. And so we have partial squared t partial x squared plus partial squared t partial y squared plus partial squared t partial z squared, okay, dv plus triple integral of, these are all the balanced derivative terms, and so they have partial w partial x, partial t partial x, plus partial w partial y, partial t partial y, plus partial w partial z, partial t partial z, okay, dw or dv, excuse me, okay, because this is a volume integral. Okay. And all this is equal to surface integral across the boundary of V of W partial t partial x dot nx plus partial t partial y dot ny plus partial t partial z dot nz dA. Okay. So that's the last step with a lot of writing, I promise. So now we can take each of these integrals here and simplify them into their vector form. Okay. And then from there, we'll be able to draw the comparison between what we get here and what we have from 1D integration by parts. Okay. Okay, so any questions on any of this so far? Okay, all right, and so this first integral, we're going to simplify it. And so instead of W times all that stuff, we're going to have W times the Laplacian of T, okay? So if you recall from last time, we went over the Laplacian operator. And so the Laplacian operator means to take the second order derivative in each direction and then add them all together, okay? This expression right here looks like we have, balanced derivatives. And so we can express this as the gradient of W dot product with the gradient of T, okay? And then down here, everything that we have in parentheses, we can express this as the gradient of T dot product with the normal hat, the normal vector, okay? And so if we put all those things together, and in fact, actually, I'm going to take this term right here, this balanced derivative term, and I'm going to move it to the other side of the equation, okay? And so putting it together in this form, that's going to give us Green's formula. Okay. And so Green's formula has the following form. And so we have a triple integral over the volume of W partial squared t dv, okay? This is equal to, first we have the surface integral term. So we have w gradient of t dot n hat dA, okay? And then we have the other term, which I moved to the other side, so it has a minus sign. And so the other one's gonna be minus triple integral v gradient of w dot gradient of t dv, okay? And this Green's formula right here, this is our multi-dimensional integration by parts, okay? All right. And so it looks like a foreign language, right? And so you have just tons of mathematical symbols just going everywhere, right? We have integrals, we have nablas, we have dot products, w's, t's, and all that stuff. But what I'm going to show you is that what we have here is exactly the multi-dimensional integration by parts. And so I'm going to draw a comparison with the 1D one, and you'll see that we have basically a one-to-one match up in between them. Okay. Okay, so let me just go ahead and scroll up. And here's our one-dimensional integration by parts, right? And so we have three components to the one-dimensional integration by parts. And so we had, on the one hand, we have the left-hand side, which is an integral over the 1D domain. And so you can think of that as like our original problem integral. Okay. Okay. And then by performing integration by parts, we split that up into two terms. And so one term, we have a term that's evaluated just purely on the boundary, right? Right, and so this is a term that's evaluated just on the Neumann boundary, okay? And then we have another expression on the right here, which is an integral over a domain, but it does so on an expression with balanced derivatives, right? And so the key here being balanced, okay? And so to recap, and so there's three parts to integration by parts. So we have our original integral, we have a boundary component, and we have a balanced derivative component as well, okay? Let's keep that in mind, and then let's kind of zip back to our Green's formula. Okay. Let's look at our Green's formula. And so on the left-hand side here, we have W multiplied by the Laplacian of T. Okay. And so this here is our original integral. Okay. Okay. And actually, the Laplacian of T, that's exactly the heat equation that and you'll see that very soon. Okay. Okay. Next, we have this term right here. So this term is it's only a surface integral, right? So everything else is a volume integral, triple integral, but this is an integral that occurs on the exterior boundary of our domain. Okay. Okay. And so since this integral only takes place on the boundary, we can say that this is exactly our boundary term. Okay. Okay. Finally, let's look at the last term, right? And so we have the gradient of W and the gradient of T. Okay. And so the gradient, maybe gradients is, maybe not something you think about every day, but the gradient you can kind of think of as representing a first order derivative, right? And so you take the gradient of a function and you get a first order derivative out of that. You just get it in vector form, okay? And so in this expression, you can see here that we have a gradient of W and a gradient of T, right? And so both are kind of equally gradientized, okay? And so this here represents our balanced derivative term. Okay. And in fact, it has the same integration bounds as our original integral, except now we move the derivatives around for it to be balanced. Okay. All right, so hopefully you see that by going through this derivation, I know it wasn't the most fun derivation. It was a lot of writing and a lot of terms, but what we get out of it is a very essential tool in our toolbox, right? So now we can take multi-dimensional problems and perform integration by parts. And so that's something that we're going to need in order to derive our finite element equations, right? And so we're going to use this to get our element stiffness matrix, our element forcing vectors for 2D, for general 2D problems. Okay. Okay. Any questions on this? Okay. All right. Of course, this is a 3D equation, and so we're not going to be doing anything explicitly 3D. Although you're welcome, you're definitely welcome to do it. Okay. And so the form that's actually going to be more useful to us is the 2D version of this. Okay. Okay. And so the 2D version looks something like this. Okay. Yeah. So that's yeah. So this is a and so the question in the chat is it possible that this is Gauss's divergence theorem instead of Green's theorem? Yeah. And so Gauss's divergence theorem, I think, is a little bit more general. And so for this one, we have the weighting function included with it. And so I think that's the contribution that Green did. And the proof that we just did and especially the proof that we just did and the derivation we just did, I think that's more attributed to Green. But yeah, but Gauss's theorem is exact same idea, except this is a little bit more specialized for finite elements. Yeah. Mm-hmm. Okay, and so the 2D version of this, and so we have a double, instead of a triple integral, we have a double integral over the area, and so we have W times gradient, or excuse me, divergence of a vector function Q, okay, dA is equal to, instead of a surface integral, we have a line integral, okay, we have W Q dot N, okay, minus double integral over the area of gradient of W dot Q, okay, dA. Of course, this is a generic form of that, and so the reason it kind of looks different from above, if you take Q and you substitute in the gradient of temperature, right, then you get exactly what you get up there. And so here we just replace the gradient of temperature with just some generic vector function Q. Okay. All right, but the idea here is the same. And so here we have our original integral. Here we have a boundary integral. Okay. Okay. But the boundary of our 2D domain is a line, and so we're going to perform a line integral there. Okay. And here is our balanced derivative extra term. Okay. And so visually, it looks something like this. And so we have our 2D domain, right? Here's our area. And then the line integral will be taken around the outside, around the outside, around the outside. Okay. Okay. All right. And so this is the form of Green's formula that we're going to be focusing mostly on because we're just going to be doing 2D problems. But I wanted to show you the 3D one because I think the 3D proof is the one that's most traditional. And I know I've talked to some people in the class. You guys are interested in developing your own 3D code, and so what you can do is you can take a lot of the methods and the theory that we do for 2D and just use the 3D equivalent of it. Okay. And so I always tell people that when you make the jump from 1D to 2D, that's a pretty big jump because that usually involves the incorporation of a lot of extra mathematical tools. And so instead of just straight up calculus, you have to think about multivariable calculus, vector calculus, vector algebra, things like that. But once you get that jump from 1D to 2D, the jump from 2D to 3D is not as big because you end up using the same tools, and so you still end up using gradients, you still end up using Green's formula, things like that. It's just that you just add an extra dimension to it. And so for this class, I focus on 2D, partly also because it's a lot easier to draw and visualize, but you can easily kind of extend this stuff to 3D. Okay, it just takes a bit more work. Okay, any questions on this before we move on to the next topic? Okay, all right, so the next topic is to take what we just learned and then apply it directly to a physical problem. And so the next topic that we're going to go over is 2D heat conduction with finite elements. Okay. And so we're basically going to learn how to solve the 2D heat equation with, with finite elements. And so, this is kind of building up the building blocks for you to do your final project. Okay. Okay. And so the first question that that you'll ask is, why are we focusing on the heat equation, right? There's a lot of other equations that we can do, right? Especially if you compare it to our ANSYS activities. All of our ANSYS activities use the structural mechanics equations, right? But what's nice about the heat equation is that it's a scalar equation. And so the solution that you get is simply just a number, right? And so that's really useful because if you were to solve the structural mechanics equation, that's a vector equation. And so, in 1D, it's no problem because in 1D, there's no concept of a vector in 1D. But once you get up to 2D, your vectors start to have two components. And so that's when things get a little bit tricky, okay? And so, there is, you guys have just seen it, right? So there is quite a lot more math involved in 2D problems there than in 1D. But I want to remind you that, at its core, we're still solving finite element problems, okay? And so to that end, the way you solve these problems, we're going to follow the exact same process, okay? And so the finite element process is not going to change, right? And so the mathematical tools, of course, are going to be a little bit more complex, but the process is still the same, right? And so let's kind of just remind ourselves of what that process is, right? And so think back to, back when we did our direct stiffness method, right? And so the methods that we did for that was first, we defined our domain. And we also, built into that, we also defined our mesh at the same time. Okay. And so that defined the problem, that defined the boundary conditions, that defined the equations, what the geometry looks like, and the mesh and all that stuff. Okay. The next step is that we took our mesh, and then for each element in the mesh, we computed an element stiffness matrix. Okay. Once we had all the element stiffness matrices for all the elements, then we would assemble them. Okay. And the point of assembly is to get a single global linear system. Okay. Step 4 is to apply our boundary conditions. Right. And so we would modify our global linear system with boundary conditions. And then once we did that, we were ready to solve. And so we would plug the matrix into MATLAB, and then we would solve our equations. Okay. when we started talking about general finite elements, we focused a lot more on the element stiffness matrix, right? And so let's go ahead and summarize, what we did in 1D for these ones, okay? Okay, and so the first thing we did was we started with the strong form of the equations, right? And so the strong form is usually, the governing ordinary differential equation, which in this case will be a partial differential equation. From the strong form, we derive the weak form, right? And so the way that we derived the weak form was we multiplied by our weighting function, and then we integrated it over our domain, okay? Okay. And then from the weak form, we derive our finite element form. And so this involved things like the shape functions, it involved like the shape function derivatives, and all that good stuff, okay? Okay. And so I remind you of this process because, we're going to be doing the exact same thing in 2D, right? And so, in particular, we've done kind of the left side of this tree to death, right? And so what I'm going to focus on for this lecture and probably the next one is how we do this process here in 2D, right? And so we're going to start with a strong form of the equations. We're going to get its weak form. We're going to use some of the tools that we just went over, okay? And then from the weak form, we're going to get our finite element form. We're going to get shape functions. And then from those shape functions, we're going to get element stiffness matrices, okay? And so just naturally with just the complexity of these problems, it's going to take longer. It's going to have more complex math, but at its core, it's still going to be the same thing. And so I really want to emphasize this because finite elements is kind of the same process, all over and over again. It's just the details of that process can be different depending on, the nature of the method that you're using or the complexity of the problem. And so I don't want you to lose sight of, what the overall kind of process is in the mathematical details, which can happen, right? And so, the mathematical details they're not trivial. And so it is quite a lot. And so, so don't get lost in it. Just kind of remember what the full process is. Okay. And so let's go ahead and start by characterizing our 2D problem. Okay, so we're going to start with step 1 right here. And so let's start by characterizing the problem domain and the boundaries. Okay. And so I kind of just drew an image like this, but here we go again. And so here's our amorphous blob, which represents a generic 2D domain. And so I'm going to use the symbol omega here to represent the domain itself. Okay. And in addition to that, I'm going to include a thermal generation function, right? And so it's S of xy. You could think of as something that's persistent throughout the entire domain. Okay. And of course, it wouldn't be a boundary value problem if we didn't have a boundary around our domain. Okay. And so I'm going to go ahead and characterize, two different types of domain or two different types of boundary. Okay. And so here, what we have is the Dirichlet boundary. And so I'll characterize that part of the domain as partial omega d, okay? It doesn't have to be just all one part. And so, I'm just kind of drawing a generic figure here, but I just want to make you, I just want to kind of define some terminology here, okay? And so the boundary, we're going to, break it up into, parts where we assign Dirichlet boundary conditions, as well as parts where we're going to specify the Neumann boundary conditions, okay? And so these are called the Neumann boundary. And so we'll call that partial omega n, okay? And so it's on the Neumann boundary that we're going to solve for, or we're going to specify a heat flux, Okay. In addition to that, as you just saw in our Green's formula, we also need an outward unit normal. Which is just basically a normal vector that lives on the boundary that points in the outward direction. Okay. And what we're going to be solving for here, what we're going to be solving for is a spatial distribution of temperature within the domain. Okay. And so that's our goal, that's our objective. And so if we solve the heat equation, that's what we're going to get. Okay. Okay. And so that's kind of the idea here, right? And so I drew kind of a generic 2D domain here, but any kind of 2D shape would work for this. Okay. And so it's a big step up. And so in 1D, we only had one choice of geometry, which was line, right? Here in 2D, we have a lot more options. All right, any questions on this so far? Okay, all right, so that's the problem domain. Now let's start to talk about the strong form of 2D heat conduction. Okay. And so I'm not going to derive this, because this is not a heat transfer class. We're mostly just going to be worried about the mathematics, right? And so the strong form of the 2D heat conduction equation looks like the following. Okay, so we have K multiplied by partial squared T, partial X squared plus partial squared T, partial Y squared plus S of X, Y is equal to 0. Okay. And so what we have on the left-hand side there is we have the Laplacian of T, okay? And so we can put this in shorthand. This is equal to K times partial squared or nabla squared T plus S of X, Y. Okay. And this is equal to 0. Okay. If you're curious about how this is derived, it's basically it's just an application of conservation of energy. And so most heat transfer textbooks will have that, but again it's not an important focus for this class. Okay, and so here's our strong form, and so this is the kind of classical way that people express the heat equation. Okay, of course because we have partial derivatives here, this is a partial differential equation. Okay. Okay, and so there are methods to solving these by hand, and in fact, I think for grad students, I think you guys take either 438 or 538, and so you guys probably been exposed to it, and so it is possible to solve these by hand, but we're not going to do that in this class. Okay, and so we're going to focus kind of primarily on the finite element, solution to this. Okay, so that's the governing equation. But of course, we also need boundary conditions for this. Okay. Okay. It wouldn't be a boundary value problem without its boundary conditions. Okay, so we have our Dirichlet boundary conditions, and so the way those work, they work just the same as in 1D. And so if we're located at the location of the Dirichlet boundary, right? And so if we hold the temperature at the Dirichlet boundary, so partial omega d, okay, then we're going to specify its temperature by some pre-specified amount. Okay, and so that's going to be T naught. Okay. Okay, so our Neumann boundary condition here takes the form of a heat flux. Okay. Right. And if you're not familiar with the term heat flux, all the heat flux basically specifies is the raw kind of amount of energy that's being pushed into your domain. Okay, and so if let's say that, I think the best example of this is that if you have your domain here and you have a heater, right? And so if you have a heater that's right next to your domain, that heater is going to be pushing heat, is going to be pushing energy into your domain. And so the way that we can model that is through a heat flux type boundary condition. Okay. All right, so mathematically, it looks like the following. And so the heat flux boundary condition looks like this. And so usually we use the symbol Q with a bar over it to indicate heat flux. Okay. And mathematically, we use a heat transfer formula called Fourier's law. Okay. And all that is that we take minus K minus the thermal conductivity multiplied by the gradient of T dot product with n hat. Okay. All right, and so what this formula basically is saying is that the heat flux in the that's coming out of the domain is solved for by taking the component of the temperature gradient in the same direction as the normal vector. Okay. All right. So that's kind of a gobbledygook of words. So let me draw that out for you just so you can see what it looks like. All right. So I call this example, but it's just a visual one. And so let's say that we have a vertical face here. Okay. And we say that we're applying a heat flux boundary condition in this direction. Okay. And so here we have heat flux that's leaving the domain. Okay. We know that it's leaving the domain because the n hat is pointing from left to right. And so we know the n hat always points outward. Okay. Okay. And so we can put a since we know that the n hat vector is pointing horizontally to the right, we can say that the component form for n hat is 1, 0. Okay. And so we also know that the temperature gradient is a vector partial phi partial x partial phi partial y. Okay. And so if we take the dot product between these two vectors, oh my God, I went back 90 minutes in time, and so I use phi from my computational heat transfer class, which is I teach right before this. So gradient of T is partial T partial x partial T partial y. I'm sorry about that. Okay, and so we take the dot product between these two. We have partial T partial x partial T partial y, dot product with 1, 0. Okay. We take the dot product between these two vectors. We have 1 multiplied by partial T partial x plus partial T partial y multiplied by 0. Okay. Of course, you multiply by 0, it's just a 0 there, okay? And so the dot product between these is just partial t partial x, okay? And so, with that in mind, we can basically form our Neumann boundary condition as q with the bar is equal to minus k multiplied by the result of gradient of t dot n. And we know what that is here. And so that's partial t partial x. Okay. Okay. And so that was just kind of a quick example of how to use that dot product. Okay. So basically, when you have a heat flux boundary condition, you have your temperature gradient. Your temperature gradient is a vector, right? And so it can point in x and y directions. And so you only are going to take the component that's facing outwards. Okay. All right. Any questions on this? Okay. All right. So that's a strong form. Okay. Boundary conditions and everything. Now let's go over the weak form for 2D heat conduction. Okay. Okay, and so remember, the way that we obtain the weak form is that we take our strong form of the equation, we multiply it by a weighting function, and then we integrate over the domain. Okay. Okay. And in this case, we have a 2D domain, and so we're going to perform a double integral, right? And then what we do from there is we use integration by parts to balance the derivatives. Okay. Okay. All right, and so we're going to follow this exact same process for this. Okay, so let me first write out the strong form of the equations. Okay, and so our strong form is k times the Laplacian of t plus s of xy, our thermal generation function. All that's equal to 0. Okay. Before we multiply by the weighting function, I'm going to take this Laplacian and put it in a slightly different form, just because it'll make it a little bit easier to apply Green's formula. Okay. And so I'm going to say this is equal to k times the divergence of the gradient of t. Okay. And so I basically just took the Laplacian and just kind of split it up into its individual operations. Plus s of xy is equal to 0. Okay. All right. So now we can multiply this and integrate. Notice how our weighting function here is a function of both variables, right? And so it's a function of both x and y because we're in 2D. And so what we get from this is we get w of x and y multiplied by divergence of the gradient of t. And we need a k there. Okay. we have a double integral dA plus integral over a w of x and y s of x and y dA is equal to 0. Okay. Okay. And so now what we can do from here is we can apply Green's formula to this first integral here. Okay, because we want to take that expression and integrate it by parts. Okay. The second integral, we can just leave it alone because there's nothing really we can do that for that one. But we're mostly interested in moving the derivatives around on this first expression here. Okay. And so if we plug in for Green's formula, this is our original integral. Okay. And we know from Green's formula, it's going to split this up into two parts. Okay. And so on the one hand, what we have is a boundary component, okay? And so our boundary component here is a line integral, right? We go from a double integral to a line integral because we have a line that goes around our boundary, okay? So w times k, a gradient of t dot n hat ds, okay? So this here is our boundary term. Okay. Then we subtract a double integral, but it's a double integral of a term with balanced derivatives. And so we moved one of the gradients onto the w, and we dot product with k, gradient of t, dA. Okay. So this term is our balanced derivative term. Okay. Oh, not equals, sorry. And so we still have this integral right here, right? So we can't forget our thermal generation term. So we have double integral of a w times w of xy times s of xy dA. Okay. And all this is equal to 0. Okay. Okay. And so we're trudging right along. And so, we performed the integration by part step. Now we just kind of have to clean this up just a little bit. Okay. But before we move on, are there any questions on any of this? Okay. All right. And so now it's just kind of clean up and substitution. Okay. The first thing that I want to highlight is this term right here, right? We have k times the gradient of t dot n hat. If you scroll up in your notes just a little bit, okay, right? We see that we have the same expression here. We have k times gradient of t dot n hat, right? And based on our definition of this, we can say that this area right here, or this collection of terms, is exactly our Neumann heat flux. Okay. And so if we scroll back down, this expression right here, this is exactly our Neumann heat flux. Okay. With a negative, I guess. Okay. And so we plug that in. We get line integral of w times minus q bar, okay, ds minus double integral a gradient of w dot k gradient of t dA plus double integral over a w of xy s of xy dA equals to 0. Okay. Okay, so the last step, I'm going to put this in a form that will, kind of make it clear what each term is going to be. And so the last thing we're going to do is we're going to take this, our balanced derivative term, and then move it over so it's by itself on the other side of the equation. Okay. And so if we do that, we end up with the following, we end up with the weak form. Okay. Right. I know I said I'm moving this balanced derivative term over to the right, but I'm going to flip the equation just because it makes it a little bit easier to read. Okay. And so on one side here, we have our balanced derivative. So we have gradient of W dot product with gradient of T dA. This is equal to minus line integral of W Q bar ds, okay, plus double integral over A of W of X and Y, S of X and Y, dA. We can put a box around this. Okay. And so this is our weak form for 2D conduction problems. Okay. All right, so it has the same form as our 1D weak form. It's just that we've had to include a lot more vector calculus here just to make sure that all the terms match up. Okay. All right. Any questions on this? Okay. All right. And so here's the weak form, but we do have to make one more requirement here, which is going to be important for us when we derive our finite element equations. Okay. Okay. And this has to do with our weighting functions, right? Remember, when we did our 1D problems with both weak form and finite element form, one of the requirements for the weak forms or for the weighting functions is that they have to disappear at the Dirichlet boundary conditions. Okay. Okay. And so basically, whatever locations that we have Dirichlet boundary conditions, the weighting function has to equal 0 there. Okay. Okay. And so, another thing that you should notice here is that, because we did our Green's theorem, our Green's formula, then we have no derivatives here higher than first order, right? And if you recall from 1D, this was kind of a big deal, because if we didn't have any derivatives higher than first order, then we could use linear shape functions or linear approximation functions for our solution. Right? And as we know, at least mathematically, linear shape functions are a lot easier to work with than quadratic. Okay, and so that's another nice benefit of this form right here. Okay. And so the next step is to basically take this equation and turn it into a finite element equation, right? And so by finite element equation, I mean that we're going to take this weak form, we're going to use we're going to plug in shape functions, and we're going to get expressions for an element stiffness matrix and element forcing vector. Okay, so let's go ahead and jump right into that. And so now let's look at finite element forms. Finite element forms for 2D heat conduction. Okay. All right, and so the goal for this part, we're going to take the weak form and then obtain expressions for element stiffness matrices and element forcing vectors. Okay. Okay. All right, and so before we do that, before we get an element stiffness matrix, we have to have elements, right? And so the first step, whenever you do any kind of finite element, anything, is to discretize your domain, right? So we have to mesh our domain. And so let's say that we have a domain that looks like this, right? So this is just our generic 2D domain, right? So here's your CAD file, here's your original geometry, right? And so if we discretize this, or if we mesh it, we would get I'm going to try to draw the same geometry here. Okay. And so we would break this up into elements that look like this. Okay. Now it looks like a peanut. Okay. Okay. And so we're not going to talk about it in detail, but if you remember when we first started talking about finite element forms, we talked about a lot of requirements that the finite element solution had to be. And so we talked about how the solution had to be continuous over element boundaries. We talked about continuity, completeness, right? So all of those same things apply here, except it's in 2D. But the upshot of all of those things is that because of the work that we did in order to get the weak form, right? We can take our equation here and solve it with linear shape functions. Okay. Okay. And so that's great news. And so that's at the bare minimum, we have to have linear functions to solve our domain, which is great. Okay. Okay. And so let's talk about something that's unique to 2D, right? And so one thing that we never got to do in 1D was that now, we have some freedom in how we choose the shape of our elements. Okay. Okay. And so, because in 1D, the only 1D element that you can have is just a line, right? But in 2D, you can have any kind of 2D shape that you want for your domain. And so, in theory, you can make any kind of 2D shape into an element, but there are popular choices. Okay. And so the ones that we focus on in this class are the two most popular ones are going to be the triangle and the rectangle. Okay. Okay. And so here we have a triangle, and in particular, we have a 3-node triangle. Okay. And the other popular choice is the 4-node rectangle. Okay. And so we'll go over both of these. And so we're going to start with the 3-node triangle. Okay. And so just as the name suggests, a 3-node triangle is a triangle that has 3 vertices. Okay? And so we characterize it, like the following. So we have our triangle looks like this. Okay. Each of the nodes of the triangle, we can label them. And so we'll call this node 1, we'll call this node 2, we'll call this node 3. Okay. Also, each of the nodes are going to have their physical location in space, right? And so node 1, we can say is located at x1, y1. Node 2 is located at x2, y2. And node 3 is located at x3, y3. Okay. In addition to that, each node here represents a node in a finite element solution, right? And so each node is going to have their corresponding solution values as well. Okay. And so we have T1. Let me use a different color for this. And so we have T1, T2, T3. Okay. For T1, T2, T3, T1, T2, T3, these are the nodal solution values. Okay. Okay. All right. And so, now that we have this new element type here, the first step is to assume a functional form for the solution, right? So just like we did in 1D. Because in addition to the nodal solution values, we need a way to interpolate those nodal solutions to any location within the element. Okay. And so we have some freedom here, and so we are going to assume a function, right? But let's choose one that kind of makes sense according to this element, right? So first of all, we have 3 nodes, right? And so that means our assumed function should have 3 unknown coefficients, right? We also want this function to be linear, right? And so, if we think of, we need a function that has 3 terms and is linear, one candidate looks like the following, right? And so what we can say is that TE here is the interpolation function across the element as a function of x and y. This is equal to A0. We have to have our constant term, so our constant term has to be there, plus A1x plus A2y. Okay. And so this function here fits all of those criteria, right? And so it's a 3 unknown function, right? And so we have 3 unknown coefficients, and every term is linear or simpler, right? So we have a term that's constant, A0. We have a term that's linear in x and a term that's linear in y. Okay. And so this function here kind of fits the bill exactly. Okay. I feel like I've been talking for a while. Are there any questions on this before we move on? Okay. Okay, and so, of course, the next step in this procedure is to solve for the coefficients A0, A1, A2. Okay. Okay. We can solve for A0, A1, A2 by requiring that our solution here matches the nodal solutions. Okay. Okay. Right, and so basically we're going to plug in each coordinate in the of the nodes, and so we're going to say that TE of x1, x1, y1 is equal to A0 plus A1x1 plus A2y1. Okay. This has to equal T1, right? Right, and so basically, if we're located at x1, y1, then we have to match the function. We have to match the value T1. Okay. Next, we have TE at x2, y2, and so this is A0 plus A1, x2 plus A2, y2. Right. And so this has to equal to T2, right? Right. And then finally, we have the we have the third condition, which is at node 3. And so we have TE of x3, y3. And so this is A0 plus A1, x3 plus A2, y3. Okay. And so this has to equal T3, right? And so we have 3 equations. We can use to solve them. We can use them to solve for the 3 unknowns. Okay. Of course, this is mathematical sadism, and so if you or masochism, I mix them up, right? And so if you want to solve this by hand, with all the symbols, be my guest. It's you're definitely welcome to do so. But this is difficult, and so and so we're going to assume that we did this, right? Whoa. Even my stylus doesn't want to solve it. Okay. Okay. And so after solving this, we're able to obtain values for A0, A1, and A2. Okay. But just like we did in 1D, we want to put this in the form of shape functions, right? And so we're going to have TE of x and y is equal to T1 and 1 of x and y plus T2 and 2 of x and y plus T3 and 3 of x and y. Okay. Right. And so we put our interpolation function in terms of the shape functions. Okay. After what those shape functions are, we have the following. And so n1 of x and y is equal to 1 divided by 2 times a, where a is the area of the triangle. Okay. And we multiply this by x2, y3 minus x3, y2 plus y2 minus y3 times x plus x3 minus x2 y. Okay. So that's n1. N2 of x and y, we have 1 divided by 2 times the area multiplied by x3, y1 minus x1, y3 plus y3 minus y1 multiplied by x plus x1 minus x3 multiplied by y. Okay. And then finally, we have n3 of x and y. This is 1 divided by 2 times the area multiplied by x1, y2 minus x2, y1. Okay. Plus y1 minus y2 x plus x2 minus x1 y, close bracket. Okay. Where A is the area of the triangle. Okay. Okay. And so it's a lot, and so this is what I was talking about earlier when, there's a lot of mathematical details here. And so, and so these formulas, I know, we've written a lot of formulas today. But, these are formulas that, remember, these are not formulas that are expected, that I expect you to memorize or anything like that. And so, what's important here is not so much the details. I mean, the details are important. But remember, it's the process that I want you guys to kind of remember this. And so if you guys can remember the process, then, the details come a lot more naturally, once you kind of, understand the process, right? And so, we saw kind of all three phases of the process today. And so, we're not quite finished yet. And so, we have a bit more to do before we arrive at the element stiffness matrix. But we saw, for the 2D problems, we saw the strong form of the equation, we saw the weak form of the equation, and now we're working on the finite element form. Okay. And so you can see here that now we have this TE of X and Y. We're going to form and so, just to kind of give you a preview of where we're going, we're going to form an equivalent expression for W, right? And so W is also going to depend on the same shape functions. And then once we have T and once we have W, we're going to plug those in to this weak form right here. Okay. And then from that weak form, we're going to derive our element stiffness matrix and our element forcing vector. Okay. All right. Any final questions before we wrap it up for the week? Okay. All right. So let's call it here. And so, I think that's enough math for one day. Right. And so when we pick this up again on Monday, we'll go ahead and finish up this derivation, and we'll look at see what the element stiffness matrix looks like for a 2D triangle. Right. All right. So thank you guys for tuning in today. Thank you guys again for your flexibility today and meeting virtually. And I will see you guys back in person on Monday. Have a great weekend, everybody.
Thanks, Dr. Tran. See you next time.
Thanks. See you next time. Aaron, Collins, you guys have any final questions? Okay. All right. So I'll see you guys next week then.